Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 24, Organic Chemistry 2. Today we will start on chapter 5, Enols, Enolates, and Aldol condensation. We will talk about acidity of aldehydes and ketones, enolate ions, keto-enol equilibria, and alkylation of aldehydes and ketones. Alpha carbon chemistry, enol and enolates. Here we have the carbonyl. According to the Greek nomenclature, this first connected carbon called alpha carbon, then beta carbons, gamma, delta, etc. The hydrogen atom protons connected to the alpha carbon atoms are called alpha protons. So hydrogens here at these positions, we call them alpha hydrogens. In the presence of catalytic acid or base, ketone will exist in equilibria with enol. So this is a ketone form with catalytic amount of acid or base. Tautomerism will occur to give enol. Ketone and enol are tautomers, rapidly interconvert. They are constitutional isomers that differ from each other in the placement of proton and the position of the double bond. So here is carbon, double bond, carbon. Here is carbon, double bond, oxygen. So they are different. We call them, they are in equilibrium. Okay? In general, the position of equilibrium will significantly favor the ketone as seen. Cyclohexanone will be in its ketonic form in 99.99%, only in the enol form 0.01%. In some cases, enol tautomer is stabilized and exhibits a more substantial presence at equilibrium. For the compound pentane 2,4-dione, we will find that the dicarbonyl presence in 10 to 30%, while in the Z4-hydroxy benta 3-ene-2-one in 70 to 90%. Because of that conjugated system, double, single, double, and this hydrogen is hydrogen bonded to this oxygen. That's why this system is stable. Phenol is an example of stable enol due to its aromaticity. So phenol here is above 99.99% in the enol form, less than 0.01% in the keto form. Why? Because you have here aromatic system, highly stable system. Acid-Catalyzed tautomerization. First, lone pair gets protonated of the oxygen. Double bond gets protonated. This protonated species is in resonance with this species. So we have two resonance structures. Okay? Then molecule of water will act as a base, taking this proton, leaving the two electrons to form a double bond and get the enol. In the basic media, base-catalyzed tautomerization, the base will abstract this alpha proton, forming an anion. This anion again in resonance with this species. Oxygen has a negative charge. Then the oxygen will act here as a base and get this proton from water to form the enol form. So, first step in acid, protonation, deprotonation. Second step, in basic media, deprotonation followed by protonation. So they are the same but in reverse order. Now let's talk about enolate. When treated with a strong base, the alpha position of the ketone is deprotonated to give resonance stabilized intermediate called enolate. So when we have base, strong base, it is one arrow here, it's not at equilibrium. One arrow here to the enolate, highly stabilized species. It's not the other going back. It's enolate, and that's stable. The enolate's called ambident nucleophile. Why? Because we have here the negative charge, and we can have the negative charge on here. They are resonance 4, right? So this species has two sides, nucleophilic sides, because they possess two nucleophilic sites. We call it ambident nucleophiles. In order to choose an appropriate base, we must take a careful look at the pKa values. Reaction of acetaldehyde with ethoxide to give conjugate base here and ethanol, this acidic hydrogen here, pKa 16.7, while for the ethanol is 15.9. They are similar, very close to each other. So we will have this reaction in Equilibria which favor the weaker acid. So it's going back 16.7, higher than 15.9. So the presence of both aldehyde and enolates is important because enolates is a nucleophile and the aldehyde is electrophile. So if we have this species in the media and we have the aldehyde also there, then we are expecting that this nucleophile will attack on this electrophilic carbon and the reaction will take place between these two. Okay? But when we have base, strong base like sodium hydride or lithium diisopropylamide LDA, then we will have the reaction one way and we get enolate. In case of hydride, we get hydrogen gas out. When we have here the lithium diisopropylamide, we will have the salt. So like here, lithium salt. And you can see clearly here pKa 16.7, here pKa 36. So this is a weaker acid, and the reaction goes this way. We have also dicarbonyl compound. here alpha hydrogen or alpha proton to each carbonyl, pKa is 9, so it's a strong acid compared to ethanol 15.9. The reaction will go to the weaker acid this way. But why this is so acidic? Good, because you have here the anion which can be stabilized by resonance to form O minus in here, this resonance structure, or we can get this one the other way around, another resonance structure. So we have highly stable anion, 3 resonance structures. Alkylation of enolates. As we mentioned before, enolates are embedded nucleophiles. They have 2 sides, oxygen negative or carbon negative. If they react with electrophile E+, they can form OE bond or CE bond. The ratio of the products of these processes can be difficult to control and depends on several factors. Solvent reactivity on oxygen may be attenuated if the negatively charged oxygen atom is hydrogen bonded to solvent molecules. When this is the case, C alkylation is favored, so polar aprotic solvents do not have hydrogen bond. O alkylation results. Countercation. Small cation like lithium ion bind tightly to oxygen, promoting C alkylation. Larger cation like potassium favor O alkylation. For 1,3-dicarbonyl substrate, the 2 oxygen atoms may chelate to the metal cation, resulting in exclusive C alkylation. Alkylating agent. For O alkylation reagent with oxygen-derived leaving groups are usually used. For C alkylation, iodides are used. Adding this all together, we can say that the best condition for C alkylation would be the use of lithium enolate in a borotic solvent with an alkyl iodide as alkylating agent. To summarize that, okay, this is the enolate structure. Oxygen has a negative, resonance structure was negative. Okay. Now, for O alkylation to be favored, hard electrophile oxygen leaving group. The leaving group here is oxygen-based, like tosylate. Large countercation like potassium, dipolar aprotic solvent to solvate the M+. Okay. For C alkylation, soft electrophiles, iodide is the best for leaving group, small countercation, lithium is the best, and borotic solvent to solvate O-. What do you mean by hard and soft? Let's just remind you with that the hardest electrophile are small, charged, and have relatively high energy for LOMO. And soft electrophiles are large, like iodide, have a little charge, and have a low energy LOMO. The student intended to carry out the following synthesis, starting with cyclohexanone. He would like to use base benzyl bromide to get this species. As you can see here, it's alpha alkylation. He or she adds sodium ethoxide to cyclohexanone in ethanol solution to make the enolate ion. Then he or she adds benzyl bromide to alkylate the enolate ion and heat the solution for half an hour to drive the reaction to completion. Predict the product of this reaction sequence. Suggest how this student might synthesize the correct product. We have to examine, as we mentioned before, we have to examine the pK value. So we wrote the reaction pK for cyclohexanone around 20 with sodium ethoxide, enolate, and ethanol, the other acid on the right side, pK around 16. Which one is weaker acid? Of course, cyclohexanone, so the equilibrium will go this way. The difference of around 4 pKa unit means that the equilibrium constant is around 10 to the power minus 4, meaning that we have only reacted 0.01% of cyclohexanone. So 99.99% of sodium ethoxide is still present in the solution. When we add benzyl bromide, then ethoxide will react with benzyl bromide via Williamson ether synthesis methodology, and we get the ester benzyl ethyl ether as a product. Also, the deprotonated cyclohexanone with the presence of the enolate in the same solution, they will react together. So we can get the ethoxybenzylbenzene or benzyl ethyl ether via the reaction of the benzyl bromide with the ethoxide. Also, the enolate will react with cyclohexanone to form this ion which protonated to get the beta hydroxy species upon heating elimination of water and forming double bond in here. To synthesize the target molecule, then the student should use a strong non-nucleophilic base such as lithium diisopropylamide LDA to secure complete deprotonation of cyclohexanone. Use an aprotic solvent, tetrahydrofuran or diethyl ether, to perform the second step. So ensure that the enolate will not protonate it. Electrical ketone, two possible enolates can be formed. One we call kinetic with less substituted. So we have here the double bond. That's 1, 2. Double bond in here. We have 1, 2, and 3. And the more substituted, we call it thermodynamic more substituted enolate. In general, it is possible to choose condition that will favor formation of either enolate. When the kinetic enolate is desired, lithium diisopropylamide is used at low temperature minus 78 degrees Celsius. LDA is a sterically hindered base and can more rapidly deprotonate the less hindered alpha position, thereby forming the kinetic enolate. Low temperature is necessary to favor the formation of kinetic enolate and prevent equilibrium of the enolate via proton transfer. When the thermodynamic enolate is desired, a non-sterically hindered base like sodium hydride is used and the reaction is preferred at room performed at room temperature. To illustrate using diagram the concept, here we have a starting material at very low temperature like 78 degrees Celsius using LDA as a base. The activation energy is small, but the enolate energy is high. Okay, so we can reach this kinetically. But if you sodium hydride at room temperature, then the activation energy is higher, but the product enolate has low energy. Here is our starting material, sodium hydride room temperature. We get the thermodynamic control, more substituted, and then when we add alkyl halide, we get the alkyl on this alpha position. Using LDA as a base at -78, we get the kinetic enolate, which is active here. So when we add R prime X, we get this product. Predict the major product of the following reactions. Here we have acetone or propanone, LDA, then allyl bromide. Of course, one expecting the alkylation in here, and this carbon. And the product will be C alkylation, this product. For this molecule, again LDA at methyl iodide. We have only one alpha proton, right? Here we don't have any proton. So the only hydrogen will be this one. Deprotonation will form the enolate. Then you add methyl iodide, you get the methyl on this carbon. If we have this molecule, we have here alpha, we have here alpha protons. Here is sterically hindered, here is not. Okay? Here is more substituted if we gonna form enolate, and here will be less substituted. Using LDA at very low temperature, we are expecting to be the kinetic product we'll get, and we get this as a measure. We can get the methyl in here, but that will be minor product. See you next lecture.